Okay, so how does all this kind of sync up with some of those examples that we saw from physics, right, of reversible and irreversible processes? Kind of let's try to put together kind of all these pieces and lemmas 1 through 3 and how they sync up with this notion of reversibility. So, again, we started with this Markov chain X, and it had a strictly positive stationary distribution pi. And we saw immediately that there was this kind of evil twin chain, right? Evil is not the right word, but there was this kind of twin chain X prime with these transition probabilities right there, and it had this quality to it that I'll read it off the board, that X prime moves backward in time, right, with the same probabilities as X moves forward in time, right, and both had to be started in pi, right, that it kind of had to make them equal, and in that sense you can certainly design examples of when you start them in different states and then it just won't quite work, but this statement of kind of the same probabilities, it's a little bit loose, but what it really means is this, this is the notion that we're really trying to communicate here, that this is a vector of xk through xl, which is a random variable, right? A vector of random variables is a random variable itself, and this, right, as we know, means equal to in distribution, right? So xk through xl is equal to in distribution to x prime l through x prime k, right? Notice I listed these forward in time and these were listed backwards in time, right? And so moving backward in time with the same probabilities as x moves forward in time, and this x prime kind of had to exist. It's sort of, if you think about this video recording analogy where you take any process, right, and if you point a camera at it and record it, immediately you sort of think, well, okay, I recorded it, but there's also, for every movie you can always play that movie backwards, right? You can always go to the end and play the movie backwards, and you sort of have this kind of reflection in a way, right? When you look at yourself in the mirror, right, there's sort of like a physical reflection, and left and right is flipped, right? The spatial dimension is flipped in some sense. X prime is sort of it's kind of a time mirror reflection, right? It's a reflection in the time mirror of X, and so it had to be there simply because any movie can be played backwards, right? And so the way to think about X is really as this reflection, but not in the spatial dimension, but in the time dimension. So why is all this important? I think in terms of definitions, hopefully you kind of follow the 3 lemmas. I've convinced you sort of on an intuitive level and on a kind of technical, right, mathematical level that X prime exists, and it has this quality to it, right, the property of being a reflection in time of X. But how does this all link up with time reversibility? Well, that really comes down to this kind of main definition here. Right, call X, right, by X I mean the Markov chain above, reversible if, right, and so here, you kind of pause and maybe not even think about this for a minute, like, when would we call a chain reversible? Well, it would be reversible when, in some sense, it was equal to its time reflection X prime, right? If we played the movie of X forward or backwards, and we couldn't tell the difference, right? If those two reflections are the same, then it seems reasonable to call X reversible, right? In this particular sense, in the sense of time, right? Time is usually not mentioned when speaking of reversibility, but that's what this is all referring to, right? When X is equal to its reflection, right, in this time mirror, right, X prime, when it's equal to it in some probabilistic sense, that's when we call it reversible, and this is what makes this notion precise right here, right? What is on the left-hand side? It's the probability that X steps from X to Y, the chain X, capital X, steps from little x to little y in one step forward in time. And what's this? This is the probability that the chain X prime, its reflection, steps also forward in time from X to Y, right? And when those two are equal, right? Notice this does not have to be true at all, right? It certainly it's not true in general, right? But when those two are the same, it basically means that x, whether you look at it going forward in time or backward in time, you just can't tell the difference, right? And so hopefully that kind of motivates this definition for you. Usually just kind of introduced in books without too much fuss about it, and we've certainly made a lot of fuss of it. So let's see. Kind of a couple of quick remarks. So in the previous lectures, I talked about entropy and the arrow of time. I mean, this is all still in the same ballpark, right? The kind of if you look back to this Ehrenfest-Ern process and specifically the entropy process that we came up with, that process is in fact time reversible. And so, that kind of gives you maybe a little bit more insight as to why that example is so such a famous one, specifically because sort of this example of an entropy that's somehow time reversible, even though it really shouldn't be. Entropy should always be increasing, should be irreversible in some sense, and it should kind of coincide with what's called the arrow of time, right? And so this again kind of shows you sort of some of the counterintuitive nature of these concepts that come out of physics, and when you kind of make them precise mathematically, you can get a lot of this puzzling behavior, and there's a lot of debates in kind of the philosophy of physics about what all this means, and you can kind of even find stuff from the 19th century with kind of all these things hotly debated. And anyway, so hopefully it's clear what a reversible chain is, and hopefully you made your brain hurt a little bit at least, and maybe hopefully even a lot. Let's wrap up maybe on this one last lemma that hopefully should kind of fill in kind of the last kind of missing piece, which is what's the link with local balance. And you can see lemma 4 here. It's saying that x is reversible, right, meaning time reversible, if and only if it satisfies local balance. Okay, so hopefully you can kind of see the proof already, right? We're gonna use the definition and basically start with this equation, right? First of all, there are two sides here, right? So I'll discuss maybe the proof going in this direction, right? Every time you see an if and only if, you want to prove both directions. So now we could prove the forward direction. We're going to assume x to be a reversible Markov chain, in which case we know this holds. And if this holds, all I need to do is apply the definition of pi prime over there, bring the pi x over, and I'm done. So this direction is a direct implication of the definition of what it means for x to be reversible, right? As soon as I write this down, and this is true, by the way, for all pairs xy, right, as would be needed. Once I write this down and once I substitute what pi prime actually is, all I need to do is bring in over the denominator, and I recover local balance, right? This directly implies local balance. Local balance. And again, local balance is often called detailed balance, but same. It's referring to the same exact condition, right? And what's the local balance, right? The condition is, right? This would imply that pi x times pxy is equal to pi y times pyx, right? That just came directly over, right? This was over here, right? If I divide this over, this is my p prime xy. So that's one direction. Now, if you want to go the other direction, right, you assume, okay, let's say my chain x satisfies local balance, which means this is true for all pairs xy. Well, then what do? I take the pi x, I divide it over, right? And what comes out here? Well, again, it's the p prime. If my p prime is here, then what I've concluded is p of xy is equal to p prime xy. And if that's true, then x must be reversible. Hence, the backward direction is also proved. Right, so lemma 4 is maybe the easiest one of all, but probably the most important one, right? It finally kind of seals the last piece of the puzzle that shows you that this deep connection between local balance and time reversibility, right? And what it all means, right? Time reversibility means that x is equal to its time reflection. So kind of the last final thing to say here is that in the kind of the homework assignment, right, the second one that's out, you'll also show that all reversible processes X can be kind of modeled as random walks on networks, right? Which is an example we've seen before, right? And sort of that gets you quite far into kind of what do these time reversible processes look like? They all look like random walks on networks, right? So anytime sort of in the future where you're stuck with modeling some process, right? So maybe you're trying to create a model for how many people are at a lunch line, right, at any particular time, right? And you ask, is that a reversible process, right? Or you ask, that is local balance satisfied, right? And is it a Markov chain even, right? So all these things hopefully you should be able to do, right? And maybe do them in a more serious setting, right? Maybe caring about how many people are in a lunch line is not all that useful, but if you're working for, say, like an insurance firm, right? Maybe you're handling how many insurance claims are handed over to the office on any given day, right? That's you can model that process as a Markov chain, and you can kind of think to yourself, is it reversible? Would it satisfy local balance? Certainly that would simplify a lot of the calculations in terms of the stationary distribution, right? And then later we'll see how the stationary distribution can kind of give us a lot of really nice calculations. Yeah, so let's wrap up here, and hopefully this was useful.